Welcome to the ChemDoctor, and this is the second video in the series that deals with mass spectrometers. And what I want to do in this presentation is apply what we learned in that first video. So if you are trying to learn about how a mass spectrometer works and then how to interpret the data, you need to see the first video in this series before you watch this one. All right, and what we're going to do in this one is we're going to assume that we have a sample of chlorine. All right, so I'll write that over here. We're going to have a sample of chlorine. Chlorine in nature is usually found as Cl2. Now, in terms of understanding how this is going to work, I am going to talk about the chlorine as if it's been converted from the Cl2 into individual atoms of Cl. Now, here's the thing. Chlorine in nature's got two different isotopes. One of them is Cl35, all right, and the other one is Cl37. All right, let me go ahead and add the atomic numbers in here. So it's Cl has an atomic number of 17. This would be the AZE notation. Now, the mass spectrometer is used in order to determine the mass of atoms and molecules, and one of its principal applications is to determine the percent abundance of different isotopes of a particular type of element. All right, and remember that an isotope is a particular atom of a certain type that has a different number of neutrons than its neighboring atom. So for example, here you're looking at Cl35 and Cl37, and these two atoms of chlorine differ in mass because they have different numbers of neutrons. So if you have a sample of chlorine, we can use the mass spectrometer, number one, to determine the number of isotopes of that particular element, and because the mass spectrometer also counts particles, we can also determine the percent abundance of the different isotopes in a particular sample. So let's go ahead and I'm going to take you through this now. So if we have this sample of chlorine, all right, I'll just circle this. We're going to inject it into the instrument, all right, and the material has to be in the form of a gas. So if it's either a solid or a liquid, when we inject it into the instrument, the first thing that's going to happen is that it's going to be converted into a gas, and that's going to be done by literally heating it up. All right. In the case of chlorine, chlorine is a gas, so it will be injected into the instrument in that form. The instrument compartment carries a positive voltage, and you can think of the gas traveling down a tube, which I'm going to call a hallway. As the gas moves through the hallway, it's going to encounter an electron beam that's being generated perpendicular to the stream of gas that's moving down the hallway. So the chlorine atoms are going to encounter this beam of electrons, which you can think of as being atomic bullets. That's a good way of thinking about it because everyone can relate to a bullet. If you get hit by a bullet, right, it's going to hurt. It's going to knock material off of you. It's going to make a hole, all those things. So the electron beam that's shooting across here is going to have collisions with the chlorine atoms, and those collisions can result in a chlorine atom losing an electron, and when that happens, the chlorine atom is going to be ionized. Specifically, it's going to pick up a positive charge. Remember that Cl has an atomic number of 17. That means it's got 17 protons. Protons carry a positive charge. The neutral atom has 17 electrons. So the net charge on a chlorine is 0. If we knock an electron off of the atom, then what we're going to have instead is going to be 17 protons and 16 electrons. And in this case, the Cl is going to be carrying a charge of +1 because there's one more proton now than there are electrons. All right. So now, once the chlorines are carrying that positive charge, they're going to be accelerated down the hallway because the hallway itself carries a positive voltage. So the chlorine atoms are going to be accelerated down this hallway, and the beam or the stream of these particles is going to be narrowed down because they're going to be essentially filtered through smaller and smaller slits. So once those atoms exit this hallway, they're in a very narrow beam of particles. And there will be a mixture in here because you're going to have Cl pluses, for example. I'll go ahead and write it in here. Cl pluses that are 35 for the mass number, and you're going to have Cl pluses which are 37. All right, and this is a mixture, and again, what we're doing is we're using the mass spec to figure out, okay, are there different masses in here? And if so, what is the percent abundance of each type? Now, once these particles reach the magnetic field, then the instrument will adjust the magnetic field to focus a particular mass of Cl against this detector, so that we will specifically isolate a certain mass of particle one at a time. All right. Now, the other thing you got to remember is that as the Cl pluses hit this detector, they are going to react with the metal there, picking up an electron and being neutralized. So the detector itself is going to be giving up electrons. And anytime we have the movement of an electron, then we have the generation of an electrical field or an electrical current. So here's the two things about the mass spec you need to remember. The magnetic field is proportional to the mass. So we can know the mass of the particle. Secondly, the electrical field is proportional to numbers. So we can know how many of a particular type of element are impinging on this detector. So we can know numbers and we can know mass. Remember that the instrument has to be calibrated against a standard. And usually that standard for atoms is going to be, C12. So the instrument first has to be calibrated so that we can tie a magnetic field or a magnetic force, right? Because we're going to be deflecting these atoms around a corner. We first have to be able to correlate the magnetic force that is causing the deflection of those particles based on a known mass, and then we can count the particles as they impinge on the detector and as they hit the detector, and as electrons move from the detector to neutralize each incoming ion. All right, so let's get back to the punchline here. We've injected a sample of chlorine gas. The objective here is to know how many isotopes we have for this particular element, number one, and number two, we want to count them so we can know the percent abundance. All right, so now let's look and see what kind of data we get out of something like this. So this might be the scan that we get for a Cl. Now, again, what I want to remind you about here is that I have eliminated the peaks that we would have for the Cl2. They're not in here because I want to keep this as simple as possible. And I see that I made a mistake here. Let me get rid of this very quickly and I'll redraw it. All right, what we're going to have for this, remember that we're looking at two different isotopes here. One of them is going to be Cl35 and the other one's going to be Cl37. So we're going to have a peak at 35, and the 35 peak rises to about 80 here. And what is the vertical axis? This is called percent intensity. And this is basically a histogram. So the tallness of my peak refers to essentially the amount of that particular isotope that we have within the sample. And then the second peak here is going to be approximately in this region. All right, and I think I'm going to go ahead and we'll change the color of that. And it's going to come up about this far. All right, now the horizontal axis is given to us in the units of mass per charge. So let me go ahead and write that down. This is mass per charge. All right, so you can see that on this axis, the larger peak is at 35. So this peak here correlates mass-wise with CL, with the mass number 35. All right, and this peak here is at approximately, and I'm just freehanding this, so you can't really see the markings very well here, but this is going to represent the peak for, this is going to represent the peaks for CL37. So this will be CL37, and you can see right out of the gate that the percentage of the CL35 isotope is much greater than the CL37 isotope. And in terms of our standard, the carbon standard is going to be somewhere down here. All right, I'm just going to use an arrow to indicate where we might find that. All right, and again, I'm not showing other peaks on here because I want to keep this simple. All right, and the CL2 peak obviously is going to be somewhere out in this region, right? Because this 40 here correlates with a molar mass of 40, and the CL2 is going to be out here somewhere around 70.9. All right, but we're just going to focus on the isotopes that are here. So the question is, how do we figure out our percent abundance from data like this, where the peaks are correlating with a percent intensity? In other words, the percent intensity here is not actually correlating directly to the percentage of the CL35 and the CL37 in the sample. So how do we get from this crude data to data that actually gives us the percent abundance? So what we're going to do to figure that out is we're going to use a formula, and I'll write it this way: percent abundance, and this is going to be equal to the percent intensity for the individual element divided by the total intensity, and then the whole thing is going to be times 100. All right, so let's see how this is going to work. All right, so we'll calculate the percent abundance for the CL35 first. All right, so for the percent abundance for the CL35, okay, this is going to be equal to, now this is the way I set this up, and I grabbed this data off of the internet. So it is actual data, it's just my scan is not as beautiful as it could be. So how do we get the percent abundance from this? All right, for the 35 it's going to be 80 for its intensity divided by 80 plus the value for the 37, which is approximately 25 here. All right, I'll put that in here so this is unambiguous. All right, so it'll be 80 plus 25. And then this is times 100. So the percent abundance, for the CL35 is going to equal about 76.2%. All right, so 76% of the sample that was injected into the instrument was composed of CL35. Now the percent abundance for the CL37 is going to equal 25. Over 80 plus 25. And this is going to equal about 24%. Now my numbers aren't adding up exactly, and that's because what I'm doing to teach this is using essentially a back of the napkin calculation, so that you can see how this works. Now, let's go back and reiterate what the goal was here. The goal was we have a sample of chlorine that has been essentially purified. So all it has is chlorine atoms in it. It's been injected in the form of a gas into the instrument. We're going to get two pieces of information out of that. We're going to get the mass of the material that we've injected, the mass of the individual atoms, and we're going to be able to count how many there are. We end up with a scan that is a histogram where each peak will have a tallness that is in proportion to the amount of that particular mass particle. And we see that the mass spec will look much like what I've diagrammed here. To find the percent abundance, we use the intensity of the individual divided by the total intensity times 100. So we see that for Cl35 it should be around 76% of the total of chlorine that exists on our planet, while the other 24% is going to be Cl37. Now, the actual numbers for the abundance are the following. I'm going to put them in here, and you can see that we were very close. This is 75.77% for the Cl35 isotope, and it's 24.23% for the Cl37. All right. So with that, I'm going to go ahead and close the video.